is something you already know as, and you maybe have heard it called slope. It's the same concept of slope. You've seen slope when we talk about how that is rate of change. Hopefully you remember the slope formula. That's M, typically written as y2 minus y1 over x2 minus x1. Typically, when you're looking at average rate of change, you're going to see it used with function notation. So you're going to see f of x2 minus f of x1 all over x2 minus x1. And this concept of average rate of change, you can use it in a few different ways. We can do it between 2 points. You can do it between 2 points on a straight line. You can do it between 2 points on any given function. Or we can even see at the end of this lecture on how we can do it between a point and then a generic distance away from it. So the first thing what we're going to do with this average rate of change formula, and we're going to be using this one right here as we work through these examples, the function notation is just going to be a little more user-friendly for us in these situations. Given the function g of t shown here, find the average rate of change on the interval from 0 to 3. And so what we're looking at is when we see that interval of 0 to 3, the fact that it says interval means that this is an x1 value and this is an x2 value. Many people confuse this with an ordered pair and go, well, how do I find the average rate of change on 1 point? This is not 1 point, this is an interval. So we are going from x equals 0, and there just happens to be a graph with this problem, to x equal to 3. So that means we're going from this point on our curve to this point on this curve, and we are trying to find the average rate of change between those 2 points. You'll notice that my average rate of change when I connected them created a completely different line. And so what we're trying to do is create what that average rate of change is. When we connect 2 points like this is called a secant line, when you connect 2 points on a curve. So we're going to go to our slope formula or our average rate of change formula. We know that that is equal to f of x2 minus f of x1 all over x2 minus x1. Now here's a reason why I'm using the function notation. So from that interval, that gave me an x1 and an x2. So then I could write 3 minus 0. But it did not just blatantly give you f of x2 and f of x1. So I need to find what is f of 3 and what is f of 0. Now that's not a big deal because on this graph, we're just going to be able to read where it is on the curve. So we can see that f of 0 has a y value of 1. And so in our next step, we could say that's 3 minus 0. So instead of f of 0, we'll say 1, and that's from finding this point right here. And then f of 3 is at 4, and so we can go ahead and plug in that function notation for that. Doing my arithmetic, that gives me 3 over 3. So the average rate of change on this interval is 1. So this is just one example on how the function notation can help you with that. And again, I just want to kind of emphasize of what students mostly miss. This is an interval right here. It's an x1, x2. We are finding average rate of change, so you need to be thinking slope. Now let's look at a second example where it's not just given on a graph. This one says, compute the average rate of change of f of x equals x squared minus 1 over x on the interval from 2 to 4. So again, let's note some keywords here. Average rate of change, we're just finding the slope between two values. Again, this is an interval, 2, 4. So this means this is our x1 and this is our x2. So really, before we ever get started, if we know that our formula is f of x2 minus f of x1 all over x2 minus x1, and we also know that our x2 and x1 value are 4 and 2, let's go ahead and find this f of 4 and f of 2 value out here to the side. Now on this one, we weren't given the luxury of just reading it from a graph, but not a big deal. What we're going to do is, you'll notice that instead of x, I have a 4 here. So that means anywhere I had an x, anywhere else in that problem, I'm just going to plug that in. And so I'm going to go ahead and set up my situation here. This is something squared minus 1 over something. And so I'm going to plug in 4 everywhere I wrote those parentheses. Now I'll just plug that into my calculator. You'll just want to use the on-screen calculator. It's the only one that's allowed. And that gives me a value of 63 over 4. The on-screen is very handy because it does give you a toggle between your decimal and your fraction. You always want to go with your improper fractions. Those are exact values. The only time you want to go with decimal is if the instructions specifically say to solve to a certain amount of decimal places. Then we're going to plug in 2, so that would be 2 squared minus 1 over something. And again, we're just going to plug in 2 everywhere. Again, you go to your on-screen calculator, and this gives you a value of 7 over 2. Now, in most situations, you might freak out when you see all these fractions. I've got 63 over 4 minus 7 over 2. But this is not a big deal. Again, your on-screen calculator, you can plug in this entire setup into that on-screen calculator. It will calculate it for you. Maybe you're a little more cautious. You may go step by step. The top part, when we subtract 63 over 4 minus 7 over 2, gives me a value of 49 over 4. 4 minus 2 gives me 2. And then finally dividing that out, I get 49 over 8. Again, I'm sticking with improper fractions. I am not going to go to decimal places unless it tells me specifically in the instructions. So for this example, it says to compute the average rate of change on the interval from 2 to 4. So we were just very basically finding slope between 2 and 4. And that gave me a value of 49 over 8. The next part we want to jump into is a little bit more vocabulary for our business sense of this. We've got 3 different vocabularies that really are going to stick with us through this course. And then if you take the follow-up course for 1325, what we're looking at is this says marginal cost. Marginal cost is defined as the change in total cost if the quantity of items produced just increases by 1. And so what's happening is the same thing's going to happen when you do marginal revenue and marginal profit. But again, it's just changing this word here. The notation for marginal cost is going to be C of Q. Your marginal revenue, marginal. So that's your cost function, your marginal cost. It's going to throw another capital M in front of it. Your revenue is noted by R of Q. So if we want marginal revenue, they'll stick a capital M in front of it. Your profit function is noted by P of Q. Now this is a capital P. Capital P is standing for profit. If you had a lowercase p, that would be your price. And then if you want marginal profit, again, you'll see a capital M in front of it. Now each of these Q's are quantity. And so you really have to know your variables and your other pieces that are going with it so that when it's cueing you on, telling you about cost, telling you about revenue, telling you about profit, you're able to either identify the equation that is given or you're able to create the equation that you need. Now for this first example, and we're just kind of easing into this, they give us a cost function of 43,000 plus 12.80 Q. And the question says, what is the total cost of 500 items? And so the fact that we are finding, here's our equation, just so I can write on top of it here. The fact that we just want the total cost of 500 items, this right here is going to be your Q. And so very simply, they are just wanting you, instead of having the Q variable, to change it to 500. So really just an evaluation of this function at 500. And so again, you're going to go to your handy dandy calculator, the on-screen one. That's the only one that is allowed for this course. And you'll just type in those values, and I would just type this in all together, and this gives you a value of 49,400. Now with these type of problems dealing with cost, revenue, and profit, it is relation to money. And so it will be 2 decimal places assumed. And so that's how you'll know how to round, because you know you're working with money. Now the next one says to find the marginal cost when producing the 501st item. And so when you're looking for the marginal cost function, remember that is the quantity of producing increases by 1. And so what we want to do first is we want to find the cost of the 501st item. We will do it just like what we did in part A, so 43,000 plus 12.80 times 501. You just plug all that into your calculator and we get a value of $49,412.80. Again, we're working with money, so we know it's an assumed 2 decimal places. Now, when it said marginal cost, we know that that's when the change in total cost of the quantity of items is produced increases by 1. So it is the change in total cost. And so we're going to do a little bit of subtraction. We're going to say, what is the cost of 501 minus the cost of 500? We already know those values from our previous calculations. And so we have 49412.80 minus 49400. Subtracting that out, and that gives me $12.80. So $12.80 is the cost of producing one more additional item from that 500. Now, this is not the overall way that we are going to be looking with each of these different functions, but it's just easing our way into some of these concepts. Now, the next thing we want to consider, we have an idea of average rate of change. We looked a little bit at our cost functions. We want to be looking at the behavior of functions just in general. And so the first part we're going to consider is when are functions increasing or decreasing. So if we have an increasing function, just to kind of define it and get everyone on the same page here, this is when your average rate of change is positive. And remember, we just talked about average rate of change. We talked about how that's your slope. So when is a function increasing? It's increasing when your slope or your average rate of change is positive. And likewise, when you have a decreasing function, this is when the average rate of change is negative. Or again, taking it back to algebra terms, this is when your slope is negative. Now, we can take this further and talk about an idea of local extrema. We talk about local extrema in two different ways. We talk about how, when do we have a local maximum value? A local maximum is when a function changes from increasing to decreasing. And so we just defined what an increasing function was, and we just defined what a decreasing function was. And so when we have a function that changes from that increasing to decreasing, so if we are increasing and then we change to decreasing, we can see that right here, this is creating a maximum. Now we do talk about how this is a local maximum because it's right, like if you just zoom into that area where it's changing from increasing to decreasing, it's not overall saying it's the maximum value of the entire function. It's just in that local area. And again, vice versa, we can say, when do we have a local minimum? Again, we're building off our previous definitions that we just stated, and that is when the function changes from decreasing to increasing. So the reverse of this. So if it's decreasing and then increasing, that means we have a negative slope and then a positive slope. So we would have a minimum right there at that change. Now it's important to note one thing here. When we're talking about increasing and decreasing, we look at the x values and we typically write that as an interval. When we're looking at a local maximum or minimum, we're talking about the minimum values, the maximum value that it's reached. And so those are going to be related to your y values. So I just want to kind of point that out here in the definitions, but let's go into this example here and see what's going on. So you can see in this graph here, we have this area where it's increasing. You can see it's going up. And then also over here, it's increasing. So if we're writing down what are the increasing intervals, we would say that it's from negative infinity all the way till this point here, again, an x value. So -2. And then we can see it starts up again here at +2 to positive infinity. We do have arrows on this function, so that's when we're going off to the infinities. When you are joining two intervals together, you do a capital U in between, and that notes the union of those two together. Again, this is where your slope is positive. And remember, we just talked about how those are only our x values. Now, we always use parentheses when we're talking about increasing and decreasing, because right here at this point, it is not increasing, it is not decreasing. So that's why we don't have any squared off brackets on that -2 or +2. Now, on the decreasing intervals, remember, this is where your slope is negative. And so if we look at that value, that's right here in between. And so that means we are looking at from -2 to 2. The next two says, let's look at the local maximum and minimum. Remember, these are going to be y values. So in these two, reminder, we just used x values to create those intervals. And in the maximum and minimum, you're going to be using y values. And so the local maximum would occur right here, and we can see that that is a value of 16. So we would say we have a local maximum of 16 at x equal to -2. So yes, I did identify where the x value of that maximum is occurring, but I just want to emphasize that we're not saying there's a maximum -2. The maximum value was at 16. Now, this is another example of why it is a local maximum, because we can see from the graph over here, it does go up higher and higher. But if we just were to zoom into this section here, that's where the graph was going from increasing to decreasing. Now, what is the local minimum? You can see that here is the local minimum here. This is where it went from decreasing to increasing. So that's at a value of -16. So we say we have a local minimum of -16 at x equal to +2. So just want to kind of clarify some notation and things that are going on with that. So when you're looking at a graph, you're getting your notation correctly. You're choosing the correct values. Even though you may be able to point and say, here it is, I want you to be able to interpret that correctly. So the next one, it says analyze the following graphs. And so we're going to do the same thing as we did in that previous example. We're going to look at increasing, decreasing, minimums, and maximums. So first thing I'm going to do is I want to look at where is this function increasing. And so I can see that it's going up from here to here, and then from here to here. Now, it doesn't matter how fast or how slow it's increasing, just the fact that it's increasing. So we would say it's increasing from a value of 1 to 3, union with 4 to positive infinity, again, because it has an arrow going off here. Then we'll look at where is this function decreasing. It's decreasing right here between 3 and 4, and then also all the way over here to 1. So we would say negative infinity to 1, union with 3 to 4. Remember, with your interval notation, your smaller number goes on the left, your larger number goes on the right, and they are in numerical order. That's why I put that negative infinity, 1 first. Now, if we want to note where are the local maximums, we would say that we have a maximum here. See, that's kind of a high point there. So we would say we have a maximum of 3. Excuse me, just did what I told you not to do. That we have a maximum of 1 at x equal to 3. Now, we don't say we have any other maximums because, yes, these are going up higher on the ends, but it's not changing from an increasing to decreasing. And then we'll say where are the local minimums at. So we have a local minimum here and here. So we have a local minimum of -1 at x equals 1. And we have a local minimum of, we're just going to kind of guesstimate 1/2 at x equal to 4. So again, you can see even my example, just be careful you are choosing that y value. Now let's look at the next function here. Again, we're going to go for all the same pieces, increasing, decreasing, maximum, minimum. So with this one, we can see, let's see, where is it increasing? So increasing right here in the middle. And so I would say it's increasing from -1 to 1. Where is it decreasing? So our function's going down. So we could say it's decreasing from negative infinity to -1, union with 1 to infinity. Where is the local maximum at? So we have a high point here. So we have a maximum of, so we're going to come over here to the y. So 2 at x equal to 1. And then we have a local minimum occurring here. Again, track it over to that y value. So negative 2 at x equal to negative 1. Now, again, we say it's a local minimum because these values are going a lot lower, but it's not changing from that decreasing to increasing. Last graph, and I want to do the last graph because it's a little bit different than the previous two. We'll do it in the same values that they did before. So where are we increasing? We're increasing here. We're increasing here. Now this one is different because we have stops on the end. So we would say, okay, where is it increasing? It is increasing from, we'll have to guesstimate here. So negative 2.5 until it gets to negative 2, union with 0 to positive 2. And then we'll look at where is it decreasing. So we've got this decreasing piece and this one. Again, just reading our graph. So we're decreasing from negative 2 to 0, union with 2 to 3. Now it asks where is the local maximum. So we have a local maximum here and here. So we have a local maximum of 16, and that occurs at x equal to negative 2, as well as x equal to positive 2. So same maximum value. And then where do we have minimum values? We have a minimum value here. So we have a minimum of 0 at x equals 0. And so we've got all of our pieces here. And so just want to kind of point out the kind of differences between these two graphs, looking at the intervals and the notations. Last example I'm going to do with you is looking at average rate of change, but in a very general sense. And it also involves a fraction, so I think we can always use a little review of that. And so it says find the average rate of change. And so again, we're talking slope. This is our interval, so this is our x1 and our x2. So I'm going to go ahead and kind of set us up here. So I'm going to have f of x2 minus f of x1 all over x2 minus x1. And so I know that I'm going to have to figure out those two individual pieces, so let's take a moment and look at those. And so let's see, f of 5. So again, we're just plugging in for this x value noted here. So sometimes I like to go ahead and set it up, and then I can just fill in my value into my parentheses. So this gives me a value of 1 over 16. Not too bad, but then we have to do f of 5 plus h. Still following your just rules for function notation. So I'm going to put a parentheses plus 11. Into that parentheses, I'm going to plug in 5 plus h. Now I'm going to go ahead and simplify this up, putting the 5 and 11 together, so it gives me 1 over 16 plus h. So when I come up into my average rate of change equation, I am going to have, instead of f of x2, I'm going to go ahead and plug in 1 over 16 plus h, minus f of x1, which is 1 over 16, all over x2, which is 5 plus h, minus 5. Now we can go ahead and clean up that bottom part there. 5 and negative 5 are going to cancel. I get 1 over 16 plus h minus 1 over 16. Now this is where I want to go over this because I want to kind of show you a little trick to help you with this. Now if you've ever added or subtracted fractions in a very basic sense, you find a common denominator. But there's a nice fraction trick that can help us with this. I'm going to show that to you. So if you ever had a fraction and you're adding or subtracting it, so I'm going to put the plus or minus. Here's a quick way to add or subtract fractions. You can multiply this way, so it gives me a times d, and then plus or minus, whatever you're doing, adding or subtracting, multiply this way, which is bc, all over multiply this direction, which is bd. And this just gives you a really quick way to add and subtract two fractions together. I'm going to use this fraction trick here for my numerator in order to put those two fractions together. So I'm going to multiply this direction, which gives me 16. Now we are subtracting it, so I'm going to say minus. I'm going to multiply this direction, which gives me a 16 plus h. I am going to put that in parentheses so I make sure I subtract the whole thing. And then multiply across the bottom, which gives me 16 plus h times 16. Now on the top, I'm going to go ahead and I'm just going to kind of clean up this top numerator here. I'm just going to work with this fraction, then bring along the division by h. So I'm going to go ahead and distribute this negative through here, which just changes all your signs. So 16 and negative 16 are going to cancel each other. So I'm left with negative h over 16 plus h times 16, all divided by h, which is probably causing some people to stress out right now. But let's come over here and also remember, so it's just kind of our remember area, how to divide fractions. When you have a fraction divided by a fraction, remember you're going to keep, change, flip, or KCF. I don't know how you were taught this, but what you're going to do is you're going to take the first fraction, and instead of dividing, you're going to change to multiplication, and you're going to flip the second fraction. So you're going to multiply by the reciprocal. So I'm going to do that here with my fractions. This gives me negative h over 16 plus h times 16. Now I'm dividing by h. So instead of dividing, I can change that to multiplication. And instead of h, this was h over 1. And so what I can do is I can just flip that and multiply by the reciprocal. Lastly, remember how to multiply fractions. When you are multiplying two fractions together, you just multiply across the top and multiply across the bottom. So when I multiply across the top here and then the bottom, that's going to give me negative h over 16 plus h times 16 times h. Now, whenever you have all this being multiplied together, you can cancel on top and bottom. So our final result is going to be, I know you're ready for the end of this problem, negative 1 over 16 plus h times 16. And typically we just leave our denominator factored like that. We don't go and distribute it. And you can, but it's not wrong to leave it factored. So you can see why I specifically want to do this example with you and give you a good rundown of remembering how to add, subtract, multiply, and divide fractions, and just go slow through your pieces. So go and try the homework for 1.3 and then reach out to your instructor if you need assistance.